Alright, let's take a look at how this Seq2Seq LSTM model is structured. Here you can see our necessary libraries and reproducibility. And okay, we start off by defining a class called Seq2Seq LSTM, and it inherits from PyTorch NN module just like any standard model. And in the constructor we are setting up an encoder LSTM and decoder LSTM. They are both regular LSTMs, but notice something here. The encoder takes in the input size, while the decoder is built a bit differently. It takes in the output size instead. That's because during training we feed the actual feature values into the decoder as input. That's known as teacher forcing. And also we are using two layers and adding some dropout between them, which helps prevent overfitting. Both LSTMs are set to batch first true, so that our input shape can be batch time features, which makes things a little easier to work with. And what can I say? I'm looking at the end of the decoder. There is a linear layer that just maps the hidden state outputs back to the shape of our targets, in this case something like a single value per time step. Okay, and in a forward method we first pass our input sequence through the encoder. This gives us the hidden state that summarizes the input. Then we run the decoder using that hidden state as the starting point. Finally, we apply the fully connected layer to the decoder outputs and return a prediction. Okay, and once we have the model defined, we need to prepare the data in a way that matches this encoder-decoder setup. The function here, create Seq2Seq data, takes care of that. So here's the idea. For every sample, we want to extract a fixed length input sequence followed by a fixed length target sequence. The input goes into the encoder and the target is what we expect the decoder to predict. Let's say our input length is 60 and target length is 30. Then for the first sample we take values 0 to 59 as input and 60 to 89 as a target. Okay, that's important. And okay, we do this sliding window style across the full sequence, and once the loops finish, we stack everything into two tensors, one for encoder inputs and one for the decoder targets. And okay, let's move on to training. Here in the train model function, we pass in the model along with the train and validation data loaders. By default, we train for 100 epochs and use a learning rate of 0.001. That's a pretty common setup for a regression task like this. We are using the Adam optimizer and the loss is MSE, I mean mean squared error, because again this is a continuous value prediction task. Now during training we loop our each batch in the training data. One important thing to notice is how we prepare the decoder input. Since the decoder needs a full sequence as input, we shift the ground truth values to the right by one time step. And then we prepend a 0 to the start just to get things going. This is like telling the decoder, here's where to start, now try to generate the next values. Okay. And then we fit both the encoder input and the prepared decoder input into the model, compute the loss, do backprop, and update the weights. At the end of each epoch, we also evaluate on the validation set, and the logic is the same. Shift the target to get decoder input, run it through the model, and collect the loss. We keep track of training and validation losses over time so we can plot them later, and to keep things safe, we also track the best validation loss and save the model whenever we see an improvement. That's okay, and here's a small thing to point out. Every 10 epochs we print the latest loss values. Just a quick way to monitor what's going on during training. And finally, after training is done, we load the best saved model from disk. That way, even if the training gets worse at the end, we still use the checkpoint that gave us the lowest validation loss. That's okay, I hope. And here you can see visualization parts for losses, I mean training, validation, loss course, epochs, legend, and let's continue. Now that the training is finished, let's move on to the evaluating how well the model actually performs on unseen data. We do that using the evaluate model function. This part is pretty straightforward. First, we switch the model to evaluation mode and wrap everything in torch no grad so gradients don't get tracked. That keeps things efficient. Then we prep the encoder input just like before. We shift the target sequence one step to the right and add a 0 at the beginning. So again, this is that teacher forcing logic during inference, except now we are doing it ground truth targets from the test set. Once we get the predictions, we convert them back to their original scale using inverse transform. And remember, we scaled all the values to between 0 and 1 before training, so we have to undo that step before plotting, and then we plot it. We only display a few samples, in this case the first 5, so we can actually see what's going on. Each plot shows the true values as solid lines and the model's predictions as dashed lines, and we label them to keep track of each sample each. And this gives us a quick visual check. If the dashed line follow the solid ones closely, then our model is doing its job. That's okay, and let's backstep and look at how all of this comes together in the run Seq2Seq function main pipeline, or here. Okay, we start by generating a synthetic signal. This is just a combination of sine waves at different frequencies, and so we have got a basic sine wave plus a slower one and a faster one added on top. The point here is to create a signal that has some structure but also a bit of complexity. It's good for testing sequence models. And next we reshape it and normalize it using min-max scaler that just squashes everything to the 0 to 1 range, which helps the model converge faster and keeps gradients under control. And after that, we create our sequence pairs using the create Seq2Seq data function. For each point in time series, we extract 60 steps as the encoder input and then the next 30 steps as the decoder target. Then we split the whole dataset into training, validation, test sets. 60% for training, 20% for validation, and 20% for testing. That's pretty typical unless we have a reason to skew the ratios. That's okay, and once the splits are done, we load them into PyTorch data loaders. These just help us iterate over the data in batches and shuffle it during training. We also define the model right here. Input and output sizes are both 1 because we are predicting a single time series. The hidden size is 64, which gives the model enough capacity to learn some meaningful patterns. And we are using 2 LSTM layers for both the encoder and decoder. After that, we call train model to fit to the model on our training set. And once it's trained, we run evaluate model to check how it performs on the test data. And finally, we just call run Seq2Seq from the main block at the bottom, and that kicks off the whole pipeline from start to finish. So this script is completely self-contained. You can run it and see model get trained on and evaluate it right away. And I think it is clean and modular. And let's look at our output. Here we have got the loss values printed every 10 epochs, and what stands out immediately is how fast the model converges. By epoch 10, the training loss has already dropped to about 0.0006, and the validation loss is sitting at 0.0002. Okay, from there the numbers keep going down and stay low. By epoch 40, validation loss is already at 0 and basically remains there. Now, zero validation loss might look suspicious at first, like maybe it overfit or the data was too easy, but we are working with a clean synthetic signal here, so it makes sense. The model is not memorizing random noise, it's learning a predictable structure. If we look at the plot below, we can see this visually. The training and validation losses both drop steeply at the beginning and then they flatten out. And the blue curve is training loss and the orange one is validation. They are almost overlapping from about epoch 15 onwards, which tells us the model is not just fitting the training data, it's generalizing well too. Now let's move over to the prediction results. This plot shows how the model forecasts compare to ground truth on 5 test samples. And solid lines are the actual future values and dashed lines are the model's forecasts. And here we can see that the model is doing a really good job of following the shape of the curves. The forecasts don't just get the trend direction right, they also match the curvature. That's important. Especially in time series, it is not just about going up or down, it is about timing and phase. Okay. And of course, there's a small lag between actual and forecast in some sequences, which is totally expected. The decoder generates values one step at a time, so small drift can build up, but overall the alignment is tight. And this result confirms what we saw in the loss curves. The model learned the underlying structure well, and it can predict future sequences that closely resemble the true ones. So that wraps up the evaluation. Clean convergence, stable validation, and accurate predictions, all signs that sequence-to-sequence LSTM setup work well for this task.